Okay. Yeah, thanks everyone for coming. And you can see this is a recruitment presentation where I'm very happy to introduce Wenjuan. She's currently a visiting scholar at UCLA, and she will be getting her PhD from Shanghai Tech University. And she has been doing a lot of work during her PhD on natural language processing, particularly on neural dependency parsing. So today, I'm happy to have her come here and introduce some of the work she's doing during her PhD. Thanks.
Hello, everyone. Sorry for the delay. And I'm very grateful to be here and to give this talk. I will talk something about the task unsupervised dependency parsing task, and I will also introduce a series of models proposed by me. NDMV model, LNDMV, D-NDMV, and EMNLP. I think some people here have seen my slides, so I will add some details about the learning algorithm or something. Okay, so for a series of models, because they have really similar characters, I call them NDMV universe. Just like the Marvel universe, just like that. Okay, so before the following talk, there is a big question that why we need discrete structures, discrete variables. Actually, we have continuous information like word vector, sentence vector, or everything vector, but these continuous vectors cannot provide us readable or controllable information. So if we want to make the generation or understanding process more, it can be controlled by human beings, there's a good chance that there's a good option that we should use discrete structures, and we may also want to model the information flow differently. So for better understanding, we will start from post-tagging. And post-tagging is to find syntactic word clusters from a set of unannotated sentences. When I said unannotated sentences, I mean that we only have a set of sentences without label of post-tag, and we want to predict. Every post-tag of the word in the sentence. And a general approach to doing this task are usually HMM. I think you know that. And HMM is a generative probabilistic model, and it has three kinds of rules: start rules, transition rules, and emission rules. And to generate a sentence and its post-tag sequence, HMM will generate by sampling a start token. Here, start. I should have a pointer here. Okay. It first generates a start token, and it simultaneously, recurrently generates the hidden variable, and then to generate the observed variable. When I say observed variable, I mean the sentence, and when I say the hidden variable, I mean the post-tag. And to optimize the HMM model, we use EM algorithm to optimize the maximum likelihood estimation. So to sum up, when we want to use HMM to learn a post-induction model, there are 3 points. One is generative model. Then we optimize it by EM algorithm. Then we go to unsupervised dependency parsing. For dependency parsing, we also learn from unannotated sentences. But here, when we say unannotated sentences, actually we have the label of the post tag. We just don't have the parse tree of the sentence. And our goal is to predict the dependency tree for the post tag sequence. And for unsupervised dependency parsing, the general approach named a DMV model. It is similar to post-tag induction because it is also a generative model, a probabilistic model, and also learned by EM algorithm, a modified EM algorithm, you can say that. So back to 2004, and I will introduce the DMV model first. DMV, as we said before, DMV model is a generative model. Actually, it is the first model that outperforms the left branch and the right branch baselines. And for the generation process, DMV model first generates a token from the root. I didn't show the root token here, but actually it is in the step 1. It first generates the first token. Then from the first token, it will make a decision whether it will generate a child token from this head token. If the decision is yes, it will generate a sentence. It will generate a token to his left, just like the step 2. And if the decision is no, just like the step 4, and it will stop generating child tokens from this head token, and DMV switch to another token to continue the generation process. To learn this DMV model, we also use EM algorithm to optimize the lower bound of this maximal, the lower bound of the likelihood. This is the performance of the DMV, and it obviously outperformed the random baseline or the left branch baseline or right branch baseline. So, as a very classic generative model, DMV actually very easily trained, can be easily trained by EM algorithms, and because we human beings also design how the data is generated, DMV model can encode many rich inductive bias like the similarity between tokens, verb and the past tense of the verb. But it also has many disadvantages. Like I divided here by 4 points. The first point is that for many post tags, they actually behave similar in the sentence. Just like the example here, I played football, and actually play and played have the similar syntax behavior. But for traditional DMV model, they didn't encode any information like this to encode the information into the sentences. So the question is how to automatically capture similarity features from between these post tags. Another question is if we can automatically capture similarities between post tags, how can we capture similarities between the words? Because obviously words has rich informations than post tags. Then the third point is for DMV model, it has a strong unrealistic context-free assumptions, and this This assumptions is actually unrealistic. So how to break this context-free assumption? And the fourth point is how to do multilingual grammar induction, because different languages mostly share some similar features on the dependency parsing. For each point, I will introduce one method to solve the problem. So I will introduce it one by one. Okay.
What does context-free means?
Okay. Actually, for HMM model, the previous hidden variable the previous hidden variable has no impact on the future hidden state if we given the current state, right? So for DMV, it is similar that the dependency, a rule, is only dependent on the two tokens it related to. It's not, it's independent on other tokens. That's why we say there's a context-free assumption. But it's realistic because for human beings, we see the whole sentence to see what is the syntactic structure of the sentence. Okay, well, I will start. This is the first model. For the similarity between post tags, the existing approaches mostly have two approaches. One is Bayesian model, and another one is handcraft features. For Bayesian models, it is too complicated, and for handcraft features, it needed some experts, some linguistic experts to design what the future is. And sometimes their futures are very useful, but sometimes it's too hard. They just define. They just define that some post tags are similar, but they did not define what is strong. The similarity is weak or strong. They didn't define this feature. So for NDMV model, okay.
So how do they add those features into a generative model?
They add the features like. They have two methods. One method is to use it as a prior, just the probability of prior, and another one is that it make it as a just if there is a future here, is a post tag feature here, it will add another future, and if the two post tag has they think that if the two post tags has similar features, they will add the similar index to this.
So sort of instead of generate the actual part of speech tag, you actually generate the feature of the part of speech?
Yeah.
Does that? Okay.
It's just like a part of speech, all part of speech, like that. So for NDMV model, we didn't use the post tag tokens. We use post tag embeddings to replace the tokens. So that we hope that the neural network can learn the similarities from similarities between post tags. This is the neural network structure of our model. Actually, it is simple. It has a 3-layer feed-forward neural network. The input is the local features. Head post tag is the local features, and the output is the probability of the rules. And the valence here is also a local feature, means that the number of child tokens this post tag already generated. And to optimize To update the parameters of the neural network, we also use maximum likelihood estimation, and different from the traditional Neural DMV, the probability of rules here is parameterized by a neural network, so it's a little different from vanilla EM algorithm. I show the learning procedure in this picture. Big P here is the probability of the grammar rules, and big E is expected counts, and big W here is the parameter of the neural networks. So for traditional EM algorithm, it is a green dotted line, and for our Neural DMV model, it is the red solid line. And for vanilla DMV model, it's just re-estimate the probability of the grammar rules by a normalize. And for our Neural DMV model, there are two steps. First, it will optimize the neural network by using the expected counts. And the objective function of the neural network is cross entropy. And the second step is to use the neural network to predict the probability of the grammar rules. That's the whole learning procedure. It's the result of our model. The two last lines is our model. It can be said that it outperforms DMV model and also the DMEM. DMEM means DMV model learned by EM algorithm, and DMV model, EM model means that it is learned by EM. I also provide a visualization of the post-tag embedding. It can be said that most of the post-tags in a post-tag family is really close to each other, like VB, VBZ, VBD, or VBP on the top right, on the top left.
What's VBP, VBZ?
VB is the original tense. VB actually is the verb itself, and VBZ is the past tense of the verb, and VBD is I will give an example like have, had, and these are two different tense.
Okay. So it's like present tense, past tense, present particular, that type of thing.
Yeah. From this picture, we can see that the similarities between post-tags can be successfully captured by our model. So if we can capture the similarity between these post-tags, we will want to capture the similarity between words. That's why we propose the lexicalized Neural DMV model. Lexicalized here means that we add some words, not just the post-tags, into this model. And this is the neural network structure, and different from the previous one. The Neural DMV model has only valence and a head word, and it predicts the probability of the child token. But it is a little different that for here we both use head word and head post tag. And it is I have to there's a note that actually for our model we do not only use we do not use all the words. Actually, we have a threshold, like a frequency threshold. Only if the word is only if the frequency of this word is bigger than the threshold, we will use this word embedding, or we will just use a post tag. And this picture is the impact of the training corpus size and the degree of lexicalization. The vertical axis is the performance. The higher, the better. The horizontal axis is the vocabulary size. The bigger if the number is big, it means that we add many words here. And different lines with different color means that we use different corpus. Actually, the yellow line means that we use the largest corpus size.
Which is how large? In your case?
It is 180,000.
And the World's Journal 10, is that 10K sentences or?
Yes, it's 10K sentences. It's a yellow one. So if we use the largest corpus size, and the performance will be 77. Okay. Until now, we have introduced the NDMV model, DMV model, NDMV model, and Lexicalized Neural DMV model. And all these three models, three models have the context-free assumption. So, how to break this context-free assumption? Actually, we propose a frame to an autoencoder frame to encode the whole sentences. And the model is autoencoder model, and the encoder is to map the sentence to a tense vector, and the decoder is to generate the sentence and its parse tree from the tense vector. Okay. This is a picture to show what I have said. The orange part means orange part is the encoder, and the blue one is the decoder. I have phi. Theta here is a parameter of decoder, and phi is a parameter of the encoder. For the encoder part, we have two approaches to map the sentence. To the vector. First one is deterministic variant. It means that the process is deterministic. Actually, here we use LSTM to map the sentence to a dense vector, and the second part is. The second approach is variational variant, which means that the process from the sentence to the dense vector S is a sampling process. This is the learning part. It's because we formalize our model to an autoencoder model. But we have to learn it in an unsupervised manner. So this pipeline shows how we improve our learning algorithm. The first line, log p x hat given x, it is a regular autoencoder objective function, and we first use JSON inequality to JSON inequality, and then use Monte Carlo. The Monte Carlo method here is like a reparameterization trick, and then we use JSON inequality again. Actually, this the second JSON inequality is just like the derivation of the EM algorithm. So for each step, okay.
What's your X here? It's the tree?
Oh, X, no.
Or the
X here is a sentence.
Sentence.
And X here is the observed variable, so it's sentence. And Z here is the hidden variable, the parse tree. And S here is the dense vector. It's the output of the encoder.
And the sentence encoded as a one-hot matrix?
Yes, it's one.
Wait, sentence encode as a one-hot?
Oh, I think. Oh, sorry. I thought it was a word. Word is encoded as a one-hot.
Vector.
But for a sentence, it's just a
bunch of those vectors.
Yeah, it can be. It's just a one-hot matrix.
Well, each column is a one-hot vector. That's what I meant. Okay.
Yeah,
Okay.
That's the input. But then you run it through an encoder, right?
Yeah, but the encoder is a LSTM, so
you will have
the one-hot matrix is as an input of the LSTM, and the LSTM will output a dense vector, which is S.
Mm-hmm. Okay.
This is the result of of our model, the two model, the red column, and we experiment our we conduct our experiment on UD Dataset. It can be said that in most cases it is larger. It outperforms NDMV model and LCDMV model. LCDMV model means left corner DMV.
Why don't you compare with LDMV, Lexicalized DMV?
LCDM. I didn't compare with Lexicalized and DMV because for our models here we did not use.
You didn't use Lexicalized.
Yeah. That's not the case. Actually, if we use Lexicalized and Neural DMV, the performance is not that good. It's mainly because it's UD dataset. There are not as much sentences as WSG dataset.
Oh, okay. So you're saying Lexicalized Neural DMV not necessarily perform better than Neural DMV just because you don't have too many sentences. So
Yeah, I think
Lexicalization don't give you a boost of the performance.
That's one reason, and another reason is that we do not have a trained word embedding for UD dataset.
Oh, for many other languages.
So yeah, so if we compare the D-NDMV model with the L-NDMV model, it's unfair, I think.
I see. Okay. And
go ahead.
Go ahead.
So I was wondering, so if instead of words, you actually gave as an input some kind of an embedding like BERT or something, wouldn't actually that help your parsing process? Or
I think it will definitely improve my results. Actually, it's my ongoing project.
Oh, okay.
Using a pre-trained language model or something.
Okay, but the way you are doing now, you are kind of simultaneously also learning the embedding of the words themselves, or the only output is this latent tree Z that comes out from the model?
Yeah, actually, in my object, I prefer to use. I prefer to use some word embeddings from BERT model or something, and then use the same architecture of Neural DMV model or D-NDMV model.
I was trying to ask, so in this experiment, your input is a sentence, a raw sentence, right? And that
a sentence is a post-tag sequence seconds.
Huh?
But the sentence is post-tag sequence, it's not a word sequence.
Oh, it's not the word. Oh, you just giving the POS sequence.
Yeah, part of speech. Yeah, that's what I was asking. Like, why don't you use the word embedding? I think her her response initially is for these data set, it was too small.
Sorry, but I don't understand. What do you mean the input is the part of speech tags? So.
Actually, if you use the word sequence, there's a question that should I optimize? Should I just fix the embedding of the word sequence, or I have to optimize the parameters of the encoder part? It's a problem, because if we want to optimize the parameters of the word vector, the number of the word embeddings are so large. So for UD dataset, I don't think it can do that.
Okay.
That's my main.
So I think this is the example. So,
okay, so
the sentence is what is next, and the part of speech is WP, VBZ, and JJ.
Yeah.
So this is not then classical part of speech tagging. So you are given a sequence of tags, and then you just basically try to find out the graphs that corresponds to this sequence.
Yeah, that's right.
Yes.
Okay. All right.
But I think that if I use the word sequences, I should be more careful about the choice of the choice of the encoder part, and how to optimize the whole structure. I should be careful.
Okay. Thank you.
So we'll talk about the last point. The multilingual unsupervised dependency parsing is to couple grammar parameters of different languages, and the key is I think the key is also to exploiting the relationships between languages. There are two existing approaches to do the multilingual grammar induction. One is just to couple all the data sets into together and train a unified neural network. And another approach is to use phylogenetic technology to combine the information of the grammar rules. And for the first approach, the problem is that language similarity is sometimes useful, but it is ignored here. And the second part is when we use handcrafted a phylogenetic tree, sometimes it is misleading. Yeah, the German. The German guy did not hear, but I will give an example here. For English, someone laughs. I think you know those
examples. There are many German guys.
Yeah, a German. I don't know his name, so sorry for that. Yes, for English, most of the time it is subject, verb, object, word vector, but word order. But for German, it is different. And he not here, but he told me that for German, this is totally sometimes different. Sometimes German is subject, verb, object, word order, and sometimes it's just like Japanese. It's verb, object, and subject. It's totally different. So I think German language is so different.
Yeah. It should be verb end.
Oh, what?
It's not verb, subject, object. It should be subject, object, verb.
Yeah. Oh, German is so complicated. Oh, sure.
But in terms of a parse tree, do they all have to be usually the same? As in the verb should be towards the root, or does not have to be like that?
Yeah. I think verb should be the root, but the thing is, when your verb is at last, then you're always pointing to your left.
Right.
Whereas if you're in the middle, you point to both sides. Then that will affect the shape of your graph.
Yeah. But the head token is always a verb. It is the same.
Okay.
And because of the context-free assumption, for a graph, we do not. Actually, the order is not matter for the DMV model, right? It is because of the context-free assumption. So for our model, we also use a neural network. Yeah, everything is neural network. And we use a neural network to we want a unified neural network to predict the grammar rules. And for each language, we use a language embedding to represent this language. So by the language embedding and the whole neural network, we softly tie the grammar parameters of different languages. And we also introduce another. We also introduce a language identification task to help to learn the language embedding. So it's a multitask learning. This is the structure of the neural network. The left, the left part. The left red part, it is just the same with the Neural DMV model, but the difference is that we add the language embedding here and concatenate it with the previous local features here, and we concatenate these two parts and put it as an input of the neural network, and the output is probability of the grammar rules. And the left part and the right part is sentence classification task. The input x1 to xn, it is a sentence, and the sentence length is n. We use a by LSTM to encode the sentence, so the input will be the input will be a sentence language, and we multiply this vector to a language embedding, then the output is the probability of language.
So here for your sentence, your X are also still the part of speech.
Yeah. Okay. Mostly we use part of speech. This is objective. The objective is divided into two parts. The first part. This is the same with the previous NDMV model. It is a log probability. It is a log likelihood, and the second part is the identification task. It is actually a classification, and L here is the sentence identification.
And so, how many languages do you consider? I guess the dimension of L is the number of languages.
You mean what is languages?
Right.
Actually, there are 15 languages, and we just select 15 languages from the UD Dataset, and so that there will be a identification. Yeah, we use EM algorithm to optimize the first part, and use the Adam algorithm to optimize the second part. Actually, for the first part, when we use the EM here, we also use Adam algorithm in the M step, just as I said in the NDMV part.
Can I ask something? So can you go back one slide? You have probability of x given g, and you have probability of I given x. Mm-hmm. The x that you feed into the second term, it's the ground truth part speech tags, or it's whatever the left one is outputting?
Actually, x here is the ground truth part of speech.
So you can optimize these two completely separately, these two objectives?
Yes. If you can totally you can fix this part and just optimize the first one, and then you can train this. You can optimize this objective separately or simultaneously.
So the
That's okay for
thetas
them.
are shared or no? Because you have a set of model parameters. They use a
The shell part is just the shell part is just the language embedding. Other part is not shells.
Wait, do you not share even a part of speech embedding?
Part of speech is also shells.
Okay.
But
So
we
you have
didn't
to
mention.
apply them together. Okay.
This is result of the multilingual NDMV model. Our model is the last two columns. This is visualization of the language embedding. From this picture, it can be seen that languages from the same language from the same language family is close to each other, but there are also some different points, like the Latin points here. Yeah. Actually, French, Italian, and Latin. These three languages is actually all Romance family, but Latin is far away from this part. It is far away from French. I think that is because that Latin is a classic language, so it is more close. It is more close to its classic counterpart, ancient Greek, but it is very far from its modern language like French or Italian. That's actually, if we use phylogenetic trees, phylogenetic trees, the relation between Latin and ancient Greek is not represented. But if we use, but it can be said that our model can successfully capture the relations of this. That's a big advantage. Okay, that's all. Any question?
It's interesting that Latin is so far from French and Italian.
Yeah, it's because that Latin is a classic language.
I see. Yeah.
Yeah, so it is very far from its modern counterparts, but it is very close to its classic part. So that's why Asian.
Yeah.
Is so.
Could you clarify how the tree is encoded in the latent space for I believe it was the D-DMV model? So I understand, so you had an autoencoder framework where you're given part of speech tags, and you're asked to reconstruct the part of speech sentence. And the latent structure corresponds to some tree, and your evaluation is based on how correct that tree is on the tree bank data set. But I don't know how,
Yeah. Actually, there are two hidden variables here. One is S and one is Z. And S is the sentence, it's just a test vector of the sentence representation, right? So S here is just a hidden variable, continuous hidden variable, and there's another hidden variable here is the dependency tree here. So to encode the whole sentence of so in order to encode the sentence information, we just So we represent the sentence, the probability of the rules by PR given S. And the vanilla NDMV model, they just use PR. So that's the difference. Also, you can see that in this picture. Yeah. For this means that the probability of this rule, and this rule, it is independent from others, right? But for this part, the rule is conditioned on the W, which is the token sentence. That's how we encode the global information. And if we and for each sentence given S and given all the probability of the sentence. If we given all the probability of the grammar rules, it is the same with NDMV model. So that's why we can do. We have all proved the learning procedure. So if we have these properties, we can predict the sentence. We can predict the sentence and the grammar, and predict the sentence and dependency tree.
Okay.
Any other questions from the audience? So you haven't talked about the future work. Do you have some thoughts on what you want to do as a future work, either, for example, extending this to new settings, or maybe work on some other problem, or design new model for the same problem? What's your thoughts?
You mean the dependency parsing future work, or the
any future work? So, for example, your future work can be, I still want to work on this problem, but I have several models that I have in mind that I will try to implement and see whether I can further improve these unsupervised dependency parsing. Or it's like, I think this is a general model because it's a generative model, right? I can use similar technique for some other task, that type of thing. Have you thought about that? And what?
Yeah, actually, this we just actually this model is this autoencoder framework is a general framework. It can be applied to any generative probabilistic model. You can. What we need to do is to replace this part to some specific structures. Like, actually, I have already applied this model to POS induction problem and also perception grouping task. Perception grouping task is a CV task. I'm not sure if you know that. It's just like it's like a picture. It's just like a significant segment, picture segment task, but it's unsupervised. So I have just applied this framework to the POS induction task and the perception task. Also, there's a paper named Compound PCFG from Stanford and Google Brain. They published a similar paper in the ACL 2019. They also use this framework, but actually this I think we proposed this model at the same time. Yeah.
Okay.
So actually one of my future research is to try to use this model to use this framework to other unsupervised AI areas. That's one future work, and another future work is just like the professor over there said. I try to use some pre-trained language model into this into this model, so we can use more lexical informations. We can use word, not just the post text, because there is a huge gap between the unsupervised dependent parsing and the supervised dependent parsing. So if we want to, make this gap more smaller, I think word information is very important.
Okay. Thanks. Great. Let's thank the speakers again.